All right, good morning. So I understand that the lecture material never gets more interesting than just after a quiz or an exam. So maybe that also is one of the sort of benefits we get from having those. But actually, really, the reason for these quizzes is that when I see that some people are not completely following up in the lecture anymore, I want to make sure that you do, and that if you couldn't solve this quiz, then go and look at the material, because otherwise the lectures to come, they're going to be all Chinese for you, or if you're Chinese, they're going to be Swiss German, which is about as difficult to understand if you happen not to be Swiss as would be Chinese. So be sure that if this quiz was easy, great, that's what the point was. But if you felt it was hard, then come and ask us, get help, so that it will be easy for you also. Okay? It should be an easy quiz for you. Okay? At least if you look a little bit more at it. There have been questions. Well, how many more quizzes? I don't know. If everybody can follow and answer questions and so on, well, then we don't need quizzes. But if then maybe here or one or there we'll have other ones. Okay, so RC circuits again, right? So the quiz was really pretty much sort of the switch capacitor or capacitor circuits. We are now into RC circuits, so there we have resistors and capacitors, and then the circuit is a little bit more complicated. We actually have to write down differential equations. We get these exponential responses and so on. But one of the great things that we can do now is we can generate clocks. And actually, one of the things, one place where we need clocks is precisely in switch capacitor circuits. So we need some kind of a mechanism that turns on and off all these switches. We certainly wouldn't want to sit there and twiddle them, right? Okay. So what is a timer? Well, the timer is something that puts out one voltage, or basically puts out a voltage pulse, right? Let's say the output as a function of time would be 0 volts, and then it goes high to, let's say, VDD. It could be 3 volts or so. Goes high for a certain period, capital T, and then it goes low again. So how would that be useful? Well, again, if you have a light, right, you push a button, the light turns on, and then after a certain amount of time, it turns off automatically again. And that, of course, is very useful because we're supposed to conserve energy, and so that will help us. If we won't forget to turn off the light, it turns off automatically for us. Clocks are very similar, except that then this action repeats automatically all the time. So a clock goes... I use this sort of nomenclature from digital. It goes high and low, but really, of course, what it does, it changes between 0 volts and, for example, 3 volts or so. And it does this all the time. For example, in your microprocessors or so, and any computer has a clock, and then this here is called one cycle, and it has some period t, right? And half the time, for example, the signal is high, and the other half it's low. So if this t was equals, for example, to 1 nanosecond, then this clock has a frequency that is equal to 1 over t, right? That would be the clock frequency. For 1 nanosecond, that would be 1 gigahertz. Okay? So these are what timers and clocks are. Okay? So now we have to build them. Okay, here is a circuit that basically does that. So what we do is we first charge a capacitor C1 from some source, and then afterwards we discharge them through some resistor or discharge. Okay? Now, of course, you may say, hey, this sounds like a recursive problem. We need a timer in order to twiddle the switches. But what we're actually going to do, and you will do that in the laboratory, what we're actually going to do is we will use the output from the timer. We'll observe this voltage VC1, and by looking at that voltage VC1, when it's high, then we will turn on switch S2, and when it's low, we will turn on switch S1. So it's not really recursive. It's just a partial diagram. Okay? But let's look about how this circuit works. Well, initially, of course, let's say the capacitor was discharged. Okay, so then we would start down here. Then let's suppose that the switch is turned on. Okay, what's going to happen? Yeah, it charges up, and it goes up to it goes up to what voltage ultimately? If we wait for a very long time, Vref, right? Because we are really then. This is a short circuit here. We are charging the capacitor through our charge and from Vref. So ultimately, it's going to reach a value Vref. Of course, it would take infinite amount of time. How is the signal going to look like? Is it going to look like this? No. Is it exponential like this? No. Right. It has to look like this because it's going to approach Vref. It's not going to somehow crash through it, right? So just by looking at the thing, we easily can determine how it has to be like, right? And based on that, of course, also we can guess what the solution might look like. What is the time constant? Which RC? But hey, you know, I want to be sure that. Yes. Okay. Or charge C1. I didn't say that, but of course I assumed that switch S2 was open, right? All right. So now let's suppose that we have some contraption here that I haven't shown in the circuit that figures out when this voltage VC1 reaches a certain level, V threshold 2. This one here, and then it turns off switch S1, and instead it turns on switch S2. Right? Can you imagine that in your head? So now, really, the reference source is completely disconnected from the capacitor, and instead we now have put our discharge across the capacitor. So our discharge is now parallel or in series. It's just two elements, doesn't matter, right? To the capacitor. What's going to happen? So we are at this point here. Yeah, I know. I know you know. Somebody else. What's going to happen? Yes. Okay. And it's ultimately it's going to reach what voltage? Yeah, right. Ultimately, of course, it's going to reach 0. So those who do not feel like answering, at least be sure that you would know how to answer this, or otherwise ask why you don't see that. Because there will be another quiz or another midterm or another opportunity where you really need to know that, and you really want to figure it out now. So yes, ultimately, of course, the capacitor is going to be completely discharged and the voltage is going to be 0. So again, how is the waveform going to look like? It's going to look like this, right? It's not going to look like that. It's going to look. Is it going to look like this? Huh? No, we actually can see that again here. Initially, the voltage across C1 is going to be large, and therefore the current through our discharge is also going to be large. So we're going to discharge very rapidly. As we get close to 0, the voltage across VC1 is close to 0. Well, it's small, right? Consequently, the current is going to be small that flows through our discharge, and hence the rate of discharge is going to be very small also. Okay? So it has to be the other way around. I want that you're able to think about it in this qualitative way, because if you're like me, a little bit mathematically challenged, well, this is a much more circuit way to understand it. Of course, we could write down a whole bunch of differential equations, and if you're good in math, you can solve them and you will get the right result. But as circuit designers, we really need to understand how the circuit works, not just the math. Okay? So it's going to look something like this. And what is the time constant now? C1 times our discharge. Right? Okay. And so it's going to take another time to reach V threshold 1, and then at V threshold 1, our miraculous circuit turns off switch S2, instead turns on switch S1, and then the whole thing repeats. Okay? So then it's going to look like this for always and ever. Okay? Until you turn off the power. Okay, a little bit of nomenclature. This thing here, when it starts from 0 or from any kind of a voltage or so, this is called the initial transient. And then afterwards, here, when it always does the same thing, that's called steady state. Which part do you think we are more interested here? Yeah, steady state, right? If you think about the clock in your computer, for example, you switch on the computer, it does this, and then afterwards it does always the same thing. It does that for billions of times, right? It's really not very, very important what exactly happens here. If it gets to the steady state reasonably quickly, we really don't care about the initial transition. So very often we'll see that also later when we analyze circuits, we're really going to analyze only the steady state. We're not going to analyze the initial transient. If there was a problem, if it took a very long time to start and so on, we might do that. But very often we don't even need to look at that. Okay? So now we are going to figure out what's happening in the steady state. Yes?
Are we manually opening and closing the switches?
No. There is actually a circuit that looks at the voltage across the capacitor VC1, and it compares it to V threshold 1 and V threshold 2. And then based on that, it turns on one or the other switches of the two switches. And again, in the laboratory 4, I guess. Have you read that already? Or? Okay, in laboratory 4, there is a timer circuit. It's a famous circuit. The 555 timer has been designed by a Swiss, incidentally, Combensind. Probably from Grison. Anyways, that timer circuit contains all that extra mechanics to turn on the switches. The switches, of course, are what? There. They're not light switches. They're transistors, right? Inside that chip, there are transistors that implement the function of these switches. And so that's actually how it's going to happen. Okay? So you don't need to do that. Yes? Okay, so that can be set again if you already looked at lab 4, then they are used as 3 resistors, or 1, 2, 3, and they set up V threshold 1 and 2, and they are 1/3 and 2/3 of VDD in that particular case. But of course, you can choose any kind of values, and so here I just didn't get into that kind of detail. I thought I'll leave that for you in the lab, so there you have another go at it. Okay, so here we just make these two voltages. You could set them up with a voltage divider or with the lab power supply, whatever you like, right? Doesn't really matter. Okay, so we're going to now calculate exactly what's happening in the steady state. Why are we doing that? What are we really interested in? Yeah, exactly. We're interested in what frequency comes out. And of course, that frequency will depend on C1 and our charge and our discharge. And then if we have to design a clock that runs at a particular frequency, well, using that analysis, we can turn that upside down and figure out what are C1 or discharge and our discharge that give us that frequency. Okay? So that's why we are doing this, or that's the goal of our analysis. All right, so now when we actually do this analysis, the circuit here on this page is a mildly complicated, or at least confusing circuit. Why is it confusing? Well, there are all these switches, and the switches can be open and closed. Now, if you're very good visually, of course, you can look at that circuit, and in your head, you can see the switches. Oh, this is open, that's closed, and so you can see the circuit configuration that you actually have. I often find that confusing, and in order to get around that, I say, well, while I'm charging, while I'm in the charging phase, then switch S1 is closed. Switch S2 is open. Really, the circuit is much simpler. It's just Vref or charge and C1. And our discharge and these two switches, they really don't matter at all. So I redraw the circuit that now captures just the charging phase. I recommend that if you have any kind of difficulties or sort of questions or so, do that also really pays. It takes a half a minute to redraw the circuit, but it's a lot less confusing then. Anyway. Okay, so now we have this circuit here, and really what we want to calculate is that it starts, the voltage starts at V threshold 1. Why? Well, because in steady state, the charging phase always starts at V threshold 1, because that's when this miraculous circuit flips the switches around. It closes S1 and it opens S2. Okay? So that's why we start at V threshold 1. And why do we stop at V threshold 2? Well, it's again, yeah, exactly, when that circuit goes and opens S1 and then closes S2. And so then we have, of course, a different circuit configuration. Okay, so we have to, so these are sort of boundary conditions here. Okay, so how could we solve this? If we wanted to know, so ultimately we want to know what is the time T1 that it takes to go from V threshold 1 to V threshold 2. How would we go about finding out what that is? Let's suppose that we know what Vref and R charge and C1 are, or at least we can give them names, right? Algebraic names. How would you go about it? Only three, I'm really doing a horrible job here. Only 3 people understand what I'm trying to explain? Gee, hey, you destroy my weekend. Help me a little bit. Is there anybody else who sees what's, or has an idea? Yeah.
Well, you can find the current because the voltage drop across our chart as your current, so V equals the integral of your current.
Okay. Right, integral and so on. We can solve a differential equation basically, right? That would be a more general way of saying exactly the same as you said. Thank you. Yeah. So, yes? Perfect. That's the other approach, right? The general approach is that we write down the differential equation for the circuit. We did that last time, so we don't have to repeat it. And then we solve the differential equation. That's a perfect way to do that. Yes?
You said there's like a circuit or something that turns it off and on.
Yeah.
Can we just put a plot on it saying, well, whenever it turns it off and on, it measures it different? And from what I'm saying, it's something that point and that point switches the circuit from one to another, right?
Yes. So could we simply drive this thing with the clock? Yes, of course we could, but then we would need a clock in order to build a clock. It's kind of defeats the purpose, right? Yeah. Okay. So all right. So we have the first solution is the differential equation, and it's fine. And you should incidentally go through at least 1 or 2 examples solving it with the differential equation. The book has a gazillion of those examples because the author of the book loves math. You may have noticed. Okay. And maybe less circuits. And I like the circuits more and less the math. But anyway, so you get 2 perspectives. Definitely go once or twice through the differential equation so that it won't be the first time on the midterm 2 or on the final exam, right? That would not be so great. All right. So the other solution that your other colleague mentioned is that, hey, we could guess what the solution is, because after all, we've solved circuits like this one, and so we could guess the solution. Now, your colleague had a very insightful guess. I put down a slightly less insightful guess. What is this? A fairly general guess would be Vc1 of t is an exponential a plus b times e to the minus t over tau. Okay, and basically the reason I wrote this down is that this kind of an equation should be able to model this kind of exponential that I drew there. of course, in the end, we have to check whether we can satisfy all of our conditions, and then we may determine that after all, this wasn't a good guess, but let's try at least. So I mentioned what conditions, what are the conditions that we have to meet? Yeah, so for example, VC1 of t equals 0, that is equal a plus, what's e to the minus t over tau? 1, right? So a plus b, and what should that be? No, where do we start? At t equals 0. This is t equals 0. V threshold 1, right? Okay? So then VC1 of t equals t1 is equal to a plus b times e to the minus t1 over tau, and that is equal to v threshold 2. Right? Make sense? Okay. And we also know, and we don't need, actually we have only two unknowns, a and b, to satisfy, so we have actually enough equations, but we can indeed write another one, VC1 of t towards infinity is equal to, actually then it's equal to a, and that is equal to, if t goes to infinity, where are we going to end up? Where would the green curve go if we never would change the switches? Vref, right? Vref. Right? And so this is another condition that has to be met. And now we actually have three conditions, and we have only two unknowns. So if we made a good guess, we can actually satisfy all the three conditions. And if we made a poor guess, if this guess here was a bad one, well, then we cannot satisfy all the conditions. I'll let you figure that out. Yes? Yes, of course. That's the... So in this case... Yeah. So. Yeah. Okay. So. So then we can determine these coefficients a and b, and then from those we can calculate what is t1. Actually, there is one other thing that is unknown in this equation that we need to write an equation for. What else? Tau. And tau is equal to R charge times C1, right? Okay, so with this set of equations, we now can solve for A and B, and then we can relate T1 to Vref and R charge and C1 and V threshold 1 and V threshold 2, okay? And then, of course, we'll have to do the exact same thing over again for the discharging phase also. All right, so we have a little bit of time, so let's try to use these last 12 minutes today efficiently to look at another idea. So we already talked about the importance of a thing called the digital to analog converters. Where do we use it? Well, for example, in that MP3 player, right? In that MP3 player, it stores music digitally, and then in order to listen to that music, we have to convert that back into an analog voltage, and we use a D2A converter for that. And we've seen we can build that out of a bunch of capacitors and switches and so an SC circuit also, but that's not the only way. And in particular, very often, we have a microcontroller, and we would like to control some analog thing, maybe a motor or something like that, or a light or whatnot. And that microcontroller actually doesn't have a D2A converter. Now, we could buy an extra part and add a D2A converter, but that would make the whole thing more expensive, right? So the question is, could we somehow simulate the D2A converter very simply if we just have a microcontroller? Well, what does a microcontroller do well? Well, basically it has a whole bunch of outputs, and all of these outputs, they can be either 0 volts or they can be VDD. These are digital outputs. And of course, we can use a program to tell them, now you be 0 and now you be VDD, right? And we can change that very rapidly all the time. Okay? So how could we use that for a digital analog converter? Well, let me get rid of this. Oh. Okay. So, well, if we wanted to output VDD, that would be very simple. We simply would tell in our program to the microcontroller, well, pull the output high and just leave it there, okay? That's easy. The other easy case is, of course, if we want to put 0 volts, then we just tell the microcontroller, make it 0 and leave it there, right, for always and ever. What if we wanted to make it to, let's say, 3/4? Right? What we really want to do is a D2A converter. We want to produce voltages that go anywhere between 0 and VDD. How could we do that? How could we make it that it goes to 3/4? Well, what about the following thing? The microcontroller really runs off a clock, right? We maybe have generated with the timer that we just discussed. So if under program control, we tell this thing to leave the output high during 3 clock cycles, then get it low during, well, I should have lined this up here. Okay, during 3 clock cycles, we leave it high, right? And then during 1 clock cycle, we go low. And then during 3 clock cycles, we are high again. During 1, we are low. My clock cycles are not exactly the same length here, but they should be, okay? Right? So what would happen? Well, the output is now high 3 times and it's low 1 time. If for example, we were to control a light with that, how would the light look like? It would look dimmed, right? Because it is not on all the time, so we're not getting as much light. Well, if we do this very slowly, the light also would flicker. But if we were to do it fast, to our eyes, it would look like it is dimmed, right? And how fast would we have to go if we were to use this for a light? Yeah, at least. At 60 hertz, maybe it would still flicker a little bit. But let's be generous, a kilohertz, 1,000 times a second. So this would be, so we would repeat this 1,000 times a second. So this would take 1 millisecond, this takes a millisecond, and so on. Is it hard to do that for a microcontroller? No, nothing. 1 kilohertz for a microcontroller, hey, that's eternity. It's extremely glacially slow. Okay? But for our eyes, of course, it's blazingly fast. They won't be able to follow. Okay, so really what we're doing here is we generate a signal that has only 2 values, but the mean of this signal is 75% of VDD. Right? And then, of course, we can do the same thing. We can make 2/3, 1/4, whatever. Yes? Oh, 50%. I thought that this one, I did this for. So how would we make 50%? Yeah, we just would go. Okay, so we can do this, and of course on the program control, and you're taking so many 61 classes that you will figure out how to write that program. We can adjust this. It's called duty cycle. Okay. Okay, so now there is a problem with this. There is a problem with this. Again, if we use our eyes, then, well, our eyes are slow. But sometimes if you were to use a motor or something like that, drive a motor with this, that would not be so good. The motor may vibrate or so, and then it gets hot, and that would not be a good solution. So the question is, could we somehow make it, could we build a simple circuit that takes this choppy thing and produces something that is much more constant? Basically, that calculates that mean. Well, turns out the simple circuit is just what we've been talking about all along, right? If if we put that choppy signal, that's VPWM, this is called a PWM pulse width modulator, right? If we put that choppy signal there, and then we run it through an RC, well, the capacitor is being charged, discharged, discharged. If we do that quick enough, much faster than the time constant of these two things, it's going to look kind of smooth, right? Okay? So, so the VPWM will look something like this. And so on. And then here, what we're really going to do is we're going to charge it for a while, we're going to discharge it, we're going to charge it for a while, we're going to discharge it, charge, discharge, and so on. Okay? And the mean is going to be just equal to the mean that we had before, right? And of course, the faster we do that, the ripple that we get there, this little bit up, little bit down, so it's going to get smaller and smaller. Okay? So now, what else do we want to do? What else do we want to know? Well, we've now come up with a circuit that can make it that this very, very choppy thing gets, well, a little bit choppy still, but not very much, right? Much less. Okay? What do we want to know? Well, now we want to design. We want to figure out how should we choose these arc charge and C1 if we are allowed to have, for example, 10 millivolt ripple or so, right? Okay. So now we have to analyze the circuit in order to determine how big is this ripple, and then hopefully you can adjust arc charge and C1 in order to make it small enough, whatever small enough is. Again, your application may require 10 millivolts, another one 50 or so, and that's how we're going to do this. All right, so the analysis is exactly the same as we just did for the timer. Right? So we again have a signal that is going to look like this. It's going to switch. It's going to change between a voltage V1 and a voltage V2. What are these voltages? Well, now they're unknowns, right? Because they're here, the lower one V1 and the upper one V2. Our voltage is going to switch between these unknown voltages, and the difference, of course, is going to be the ripple. Okay, so then we'll have to solve for this. Well, of course, the entire characteristic is going to look like this, where this goes up to VDD, ultimately. And again, we can make a guess. VC1 of t is equal to a plus b times e to the minus t over tau. Exactly the same as we did already. Look, this is actually quite universal, quite useful. And then we know VC1 of 0 is equal to V1 is equal to a plus b, and so on. We've done this already, right? It's exactly the same analysis. Ditto for the discharging phase. Oh, the circuit is not quite right here. The discharging phase now, this would be VPWM now is 0 volts, right? Okay. So we are discharging, and so then we are going down from VDDD and on a path like this. And we want to know that time T2 it takes to go from V2 to time T, whatever I call it there, T2. So Vc of t again is a plus b times e to the minus t over tau, I guess. And then Vc of t equals 0 is equal to a plus b. And what should that be equal to? V2, right? And Vc of T2 is equal to V2 and so on. Okay. All right. So then afterwards we can put these two together, right? We know now that during the first phase we are charging, during the second phase we are discharging, And these are basically the solutions with these initial conditions plugged in. Now, what are the unknowns here? Well, the unknowns are V1 and V2, right? We know the time constant. We know the times here. Why do we know the times T1 and T2? Why do we know those? They come out of the microcontroller, right? The microprocessor makes that. It sets up the PWM signal. So, of course, we know what they are. But what we don't know now are V1 and V2. So we have this equation, has two equations, two unknowns, V1 and V2, and we can solve for those. So, and then we can plot as a function of the ratio of T1 over T1 plus T2, we can draw what is the mean voltage. V mean is equal to V1 plus V2 over 2. And that should be, well, we should just start at 0, right, when T1 is equal to 0, and we should end up at VDD, 100% of VDD, when T1 is equal to T, the entire cycle, and T2 is equal to 0. In between, it should be linear. And that's what I got when I solved for the problem, and you can try this also. Now, we also might be interested in the ripple. That would be V2 minus V1, right? Ideally, what comes out of our D to A converter is a constant, right? When we've set it to a certain duty cycle, then the output should be constant. Well, it's not, because in practice, of course, the capacitor is being charged a little, discharged a little. It just happens so fast that it's just a little charging and discharging. So we're getting ripple, and that ripple depends on the duty cycle. Where would you expect? So if the duty cycle is 0, so the output of the microcontroller is always 0, what do you expect the magnitude of the ripple to be? 0, right? 0, exactly, and that's also what the analysis said. Same thing here. In the middle, somehow we get the peak ripple. One last question. So we analyze this, and for certain values for R and C, we get the ripple characteristic that looks like this. Now, here apparently the ripple is about 2.5% of full scale. What would we have to do if we wanted to cut down the ripple? For example, 10x. Yeah, for example, we could increase the capacitor or the resistor, either of these two. And that's what I did here. I changed the time, basically the time constant, right? And as I increase the time constant, I go down and my ripple gets smaller. What's the disadvantage of making the time constant very long?
Longer to get to the steady state.
Yeah, exactly. Of course, if the microcontroller wants to switch to another output voltage, then it's going to take the output eventually will get there, but it's going to take forever for the capacitor to be charged to that new value. All right? So these are RC circuits. They're very useful. And some examples of that.